All right, let's just jump right in. We are literally swimming in light every single second of our lives. But what even is it? I mean, really? For centuries, that super simple question sparked one of the biggest, most heated debates in all of science. So today, we're going to play detective and investigate the incredible identity crisis of light, a mystery that didn't just stump physicists, it completely rewrote the rules of reality itself.
So here it is, the central question. The whole mystery in a nutshell. Is light a wave, kind of like a ripple spreading across a pond? Or is it a particle, like a tiny, tiny bullet of energy shot in a straight line? You see, these were our two main suspects, and for the longest time, everyone was convinced it just had to be one or the other. No way it could be both.
Think of it this way. The wave theory says light is this smooth, continuous flow of energy. You drop a pebble in a pond and those ripples just spread out everywhere. But the particle theory, totally different. It pictures light as a stream of individual little packets, like a super fast pitching machine launching microscopic baseballs. You can't get two more opposite ideas, right?
To solve any mystery, you need clues, you need evidence. So let's start with the first huge piece of evidence that came along. A clue so powerful that for a while there, it looked like it had solved the entire mystery. Case closed.
And this clue comes from a really clever experiment, first done by a guy named Thomas Young way back in 1801. It's called the Double Slit experiment. And the best part is how simple it is. Seriously, you just take a beam of light, you shine it at a wall that has two little slits in it, and then you just look at the pattern it makes on a screen behind the wall. That's it.
Now here's the logic, and this is the really cool part. Imagine you're shooting particles, like say bowling balls, at two open garage doors. What would you expect to see on the back wall? Just two lines where the bowling balls hit, right? Simple. But what if you sent a water wave toward those same two openings? Well, two smaller waves would go through, and they'd spread out and start crashing into each other, creating this complex rippling pattern.
And this is what they saw. It wasn't two simple lines at all. It was a whole series of bright and dark stripes. This is called an interference pattern, and there's only one way to get it. Waves have to be interfering with each other, building each other up in some spots and canceling each other out in others. This was it, the smoking gun. Light had to be a wave. So for almost 100 years, that was it. The case was considered closed. The evidence was right there, it was undeniable. The entire scientific world just kind of moved on, totally confident that light was just an electromagnetic wave. End of story. Or so they thought.
Because just when everybody got comfortable with the idea of light being a wave, a brand new, totally baffling clue showed up from a completely different type of experiment. And this new clue presented a mystery that the wave theory just, well, it had no answer for.
This new mystery was called the photoelectric effect. The idea is simple enough. You shine a light on a piece of metal, and if the light is right, it can actually knock electrons right off the surface. Now, common sense and the wave theory would tell you that a brighter, more intense wave of light should hit those electrons harder and knock them out easier. But that's not what happened at all.
Okay, imagine you're at a vending machine that only takes $1 bills. Low-frequency light like red light is like trying to pay with pennies. You can turn the brightness way up, that's like throwing a whole bucket of pennies at the machine, but nothing's gonna happen. 0 electrons pop out. But if you use just a tiny bit of high-frequency light like ultraviolet light, that's your dollar bill, and bam, an electron pops out instantly. It wasn't about the brightness at all, it was all about the frequency.
So, in 1905, this guy Albert Einstein comes along, and he proposes the only explanation that actually works. He said maybe light isn't a continuous wave. Maybe it shows up in little individual packets of energy. He called these packets quanta, and today we call them photons. And the energy of each photon is directly tied to its frequency, which perfectly explains our vending machine problem.
And there was even more evidence. Another scientist, Arthur Compton, showed that when a high-energy photon slams into an electron, it literally bounces off like one billiard ball hitting another. It transfers some of its momentum and changes direction. A wave just doesn't do that. This Compton scattering was another giant checkmark in the light is a particle column. Okay, let's pause. We've got two sets of clues. The double slit experiment screams that light is a wave. The photoelectric effect and Compton scattering are shouting that it's a particle. They directly contradict each other. They can't both be right, or can they? And the verdict is, honestly, one of the weirdest and most mind-bending conclusions in all of science. What is light? It's both, and at the same time it's neither. It behaves like a wave when you set up an experiment to measure its wave-like properties. And it behaves like a particle when you set up an experiment to measure its particle-like properties. This is the absolutely wild idea of wave-particle duality.
So if your brain feels a little bit twisted into a pretzel right now, don't worry. You are in very good company. The legendary physicist Richard Feynman once said that this one phenomena contains the only real mystery of quantum mechanics. This isn't some side story. It is the central puzzle of how our universe actually works.
So, okay, it's weird. Why does this bizarre identity crisis actually matter to you and me? Well, because once we stop trying to force light to be one thing or the other and actually embrace the weirdness, we learned how to use it. And learning how to control that weirdness has changed absolutely everything. By leaning into the particle nature of light, we can now build incredible devices that can literally fire one single photon at a time. Think about that. This isn't sci-fi. This technology is the foundation for things like quantum key distribution, which creates communication networks that are physically impossible to eavesdrop on, and it's a critical piece for building the next generation of quantum computers.
And this is not just some theory on a blackboard. We are actually engineering with this stuff. Look at this tiny machine. Get this, it is being physically pushed around by quantum forces that come out of completely empty space. This is a real thing called the Casimir effect, and it's stone-cold proof that this quantum weirdness is real enough and powerful enough for us to build with. So, what's the big picture here? Solving light's identity crisis was never just about answering some obscure physics question. It's like being a chef who finally discovers the one secret ingredient in a legendary recipe. Once you know what it is, you can not only perfect that recipe, you can invent 1,000 new ones you never even dreamed of. That's exactly what understanding wave-particle duality has done for us. And that really leaves us with one final huge thought. We figured out that something as basic as the light we see every day has this bizarre, impossible, dual identity. So it just makes you wonder, if the fundamental rules of our universe are this strange, what other mind-blowing principles and world-changing technologies are still out there, just waiting for us to find them?